Hello, I'm Harold Russell from Photonic Systems Incorporated. Today I'm going to demonstrate the prototype star module which PSI recently fabricated for one of our Navy customers. Connecting this module between an antenna and a sensitive receiver allows signals to be received at all frequencies between 500 megahertz and 18 gigahertz, even when a very strong signal, anywhere between 700 megahertz and 2.7 gigahertz, is being transmitted from a co-located antenna. This diagram on the board here shows the intended operation and is a good introduction to the demonstration I'm going to run today. Here, in this blue antenna, we're listening for a signal between 500 megahertz and 18 gigahertz being transmitted from a distance antenna shown here in green. But right near the blue antenna, we have a transmitting antenna that's shown here in red. It's transmitting a strong signal between 0.7 and 2.7 gigahertz. Prior to the transmitting antenna, we have a coupler tapping off a reference copy for the interference reference RF port of the star module. The star module uses this reference copy, subtracting a correctly weighted copy of it from the total signal picked up at the receiving port. In this setup we'll be using to demonstrate the star module, we do not have antennas. So the signals will be routed with cables and combiners shown here in the diagram. So here is the laboratory setup. The signal generator here is the transmitting generator with a power amplifier that sends a transmit signal between the frequencies of 0.7 to 2.7 gigahertz. This coupler here is used to tap off a fraction of the signal power to serve as a reference copy of the transmitted signal for the interference reference RF port on the star module. Of the remainder of that transmitted, some of the transmitted signal will show up on the receive antenna as mutually coupled power. And in this setup, we simulate this by connecting the other output port of a tap coupler to one of the input ports of the RF signal combiner, connecting to the antenna RF port of the star module. Here's the star module RF port connection. During this demonstration, the transmit signal powers at this port are going to be plus 10 dBm. The other input port of the coupler is used to supply a second signal generator with a signal of interest without an amplifier. The power of the weakest signal at this port is only minus 24 dBm. The protected RF receive port on this star module is underneath. We are now connecting this signal to the spectrum analyzer to give you a visual look at the signal levels. The module is controlled by software that's running on this computer. And it's connected to the module through a tuning and control port that's underneath the module. Also, the DC power supply is giving power to the module underneath. Star module is in what we call a bypass mode, simply sending all of this signal to the spectrum analyzer right through the module. Looking at these signals on the spectrum analyzer, right now we see a strong signal that's at 2.625 gigahertz, plus or minus 5 megahertz, originating from the power amplifier at the output of the transmit signal generator. In this demo, we are not putting true communication signals on our 2.625 gigahertz carrier, but simply a constant 10 megahertz frequency modulation. If we turn off the transmit signal generator for a moment, we'll be able to see the signal of interest on the scope, on the spectrum analyzer. What we'll notice is it's roughly 30 dB below the higher signal that's being transmitted. I'm going to turn back on the transmit signal generator, and now we can see that we cannot see the signal of interest. Now from the module control switch here, I will switch the module into what we call the star on mode. And sure enough, in this mode, the module looks at the copy of the strong transmit signal coming into the module at the interference reference RF port and subtracts it from the total signal at the antenna port. And sure enough, on our spectrum analyzer, we can now see our received signal of interest showing up clearly now that the star module has suppressed the strong interference signal. I can move around this signal of interest in frequency and show that I do not interfere with any of the cancellation at all. As you can see, I'm moving the signal of interest around in frequency and not interfering with the canceled transmit signal. Finally, to qualify how well the module cancels the transmit signal, let's for the moment turn off the received signal of interest and look just at the remains of the canceled transmit signal. So that's the level of the canceled signal. And right now we're showing a 10 dB per division. And so I'm going to show you now back with uncanceled signal. So roughly we're seeing about a 40 dB cancellation on the spectrum analyzer. At other frequencies in the 0.7 to 2.7 gigahertz cancellation bandwidth of this particular module, we have measured as much as 65 dB of cancellation in a 10 megahertz bandwidth. In this demonstration, we're now going to change the center frequency of both the transmit and the signal of interest out of the generators, and we also changed the spectrum analyzer prop. So here on the spectrum analyzer, we can see that again we have a new center frequency of 1.5 gigahertz, and we have the same 10 megahertz of FM bandwidth at 1.5. There is the strong transmit signal in the bypass mode. If I shut off the transmit signal, you can see the signal of interest again. It's roughly 30 dB below this transmit signal that's stronger. So I am going to now again put the module control switch from the bypass into the star on mode. And now you can see the signal of interest right in the middle of the transmit signal. Again, I can change that frequency and move it around. And I'm not changing the cancellation at all of the strong transmit signal. To give you a better idea, again, also of how well it's canceling, this is the canceled signal at 10 dB per division. You can see that I can, so here's the uncanceled signal going directly straight through the star module. And with the star module on, you can see I'm roughly better than 40 dB of cancellation of the transmit signal. Thank you.